So now let us start part B, efficient polynomial evaluation. So you can see from this title, we want to solve a simple computing problem. So what's that computing problem? Polynomial evaluation. All right, so let's start with part B.1. Let me describe this problem first. All right. First, let's look at our problem number 1 for this class. Evaluate a polynomial. Yeah. Given a polynomial, we use this expression, the standard expression for a polynomial. P of x equals a0. We have set of coefficient a0, a1 through an. Yeah. Then we have variable x. Okay? Yeah. So you can see we have a sequence of additions. For each term, we need to do multiplications. Yeah. So now the question. Yeah. All right. So here for the coefficients, a0, a1 through an, usually when we select coefficients, given an array of coefficients, then we fix the coefficients. Then we change the variable, so we can change the values for the variable to different values. Then we can evaluate this polynomial. And because the coefficients we treat as parameters, so if we like, we can change to different coefficients as a different array of, parameters. Yeah. Then our goal, we need to evaluate P of x efficiently. Yeah. So here, this word efficiently is very important. Yeah. Because for this problem, it is pretty easy. If you want to find the correct answer, that is very easy. But here our main concern, do it as fast as possible. That is the main challenge. You may have many different ways to do it, but we want to find the fastest way to solve this problem. All right, so let's look at the, solution, do some analysis for the solution. The first thing, after part 1, we get some basic understanding of the algorithm. Here the question is, do we really need an algorithm here? Because it is so easy, the problem so easy, why we need an algorithm? Right? Yeah. So let's try to answer this question. Yeah. We know in order to evaluate a polynomial, we only need to do addition operations and the multiplication operations. Okay? Only these two types of operations. Yeah. So the first question, because when we talk about efficient evaluation, how do you measure efficiency, right? How do you know one algorithm is efficient, is more efficient than another one, right? So you need a special measure for that efficiency. Yeah. The first straightforward answer, execution time. We can look at the running time. So you hit the enter, so then look at the response time, right? So it's very easy to use the execution time as the measure. But here, although it is pretty convenient to use execution time, but it may not be a stable measure. Here, I want to give you this concept. So this measure not stable. So what do you mean not stable? First, it relies on the computer you use. Do you use a supercomputer or you use some very cheap low-end computer? Right? Yeah. So, and also some other factors possible. Yeah. The programming, the programmer's programming skill also can make some change. Yeah. So that kind of factors, if you put in, then the execution time you measure could be different. Yeah. So for that reason, we may feel, so our first consideration, this execution time may not be a good measure. So we like to consider a more stable measure here. Yeah. So then the next one, using number of additions and a number of multiplications. Okay, so this is the second idea. Count the numbers, number of additions and a number of multiplications. You can see if you use this way, it's more stable, right? Yep. Because it does not rely on your machine. Supercomputer, low end, doesn't matter. Another thing is it does not rely on the programmer's skill, right? A good programmer or a bad programmer, no difference. If we use this measure, you can see much more stable than the previous one. Okay. All right, so here you can see we get a little better understanding on that efficiency. Now, later we will spend more time on that efficiency. All right. So now we try to solve this problem. So I will first try to solve this. Let's solve it. Let's get a solution first. We just use the straightforward algorithm. So what do you mean straightforward? The one everyone knows how to do it, right? Yeah. Anyone who does not know how to evaluate a polynomial, is there anyone? Yeah. I don't think there is anyone in our class who does not know how to evaluate a polynomial. Okay? Too simple. Yeah. Straightforward method. Yeah. But this straightforward method, we have a formal name for it, official name for it. And later in our module 3, we will spend some time to learn this kind of straightforward method. So it is called brute force method. Yeah. Brute force method. All right? So actually here, we just use the brute force method. Okay? Yeah. When we use the brute force method, let us work on each term. We know each term, right? Term by term. There are many terms. Term by term. Each term. Yeah. This is a good representation for a typical term. A sub k times x to the kth power. Yeah. And to evaluate this value, we only need to do multiplications. Yeah. But the question is, how many multiplications do you need for this evaluation? Okay, yeah, think about that. Yeah. All right, so this is our first small problem to solve, small subproblem to solve. Original problem, polynomial evaluation, right? In order to solve that relatively big one, we need to solve several smaller subproblems inside it. So this is the first one. Yeah. All right. But this one, I will delay a little bit. Although it is pretty simple. Yeah. You can try the number of comparisons, not comparison, the number of multiplications here. Not comparisons. Later we will have a lot of computing problems. We need to use comparisons, but not here. Here we do not need to use any comparison. Yeah. Addition and multiplication. Yeah. But I delayed this counting problem later a little bit. Yeah. So let us do some other things first. Yeah. First, let me give you the reference of this problem. So you can see I jumped to our textbook section 6.5 on page 234. Yeah. The reason is simple. I feel this problem is the best for our Module 1 introduction. Is the best. In my opinion. Why is it the best? Because it can impress you a lot. Later you will see. The result is very impressive. The result is very impressive. So I need that impressive algorithm in our Module 1 to give you a good impression. Yeah. All right. Yeah. The question, is your algorithm efficient? Yeah. Here we assume we have solved this problem. Yeah. Because we know how to find the answer. So we have solved it. Yeah. The next question we need to ask, is your algorithm efficient? Yeah. For this class, we always need to ask this question. Whenever we solve a computing problem, we need to ask this question. Okay? Yeah. So in order to get an answer, you need to do something. Yeah. All right. So another question immediately after the first question, this one, are we satisfied with this solution? Think about yourself. Are you satisfied with the solution? Yeah. I guess for 90% of our class, you may like to say, yes, we're satisfied. The reason is simple, because that's the only algorithm, the brute force method, that's the only one we know. If we are not satisfied, we do not know how to do better than that. Nobody knows how to do better than that. So we have no reason to say we're not satisfied, right? That's probably the obvious reason. So most students may like to say yes. Yeah. All right. In order to answer this question, we need to do a lot of analysis work, a lot of comparisons. After we see the comparison result, then we can have a better answer. Yeah. All right, so we need to delay this question. Yeah. All right. At this point, we do not know how bad it is, right? Also, we do not know how good it is, how bad it is. We know nothing. Okay? So that means we need to do some work. We need to do some analysis work. Okay? Yeah. What kind of analysis work? Here, find the performance number of this algorithm. Performance number. What is the performance number? As I pointed here, number of additions and multiplications. That is the meaning here. Okay. the performance number. Okay, we need to do that. Yeah. All right, so let me go to the next screen. So we try to do that. Yeah. Although in this video, we may not be able to complete that analysis, but we will, do some significant amount of work toward that goal. Yeah. All right, the goal, find the number of operations. Yeah. All right. Here, in order to make the comparison look reasonable, so here we need to make some reasonable assumptions. So in research, in problem solving, in research, many times we may need to make reasonable assumptions. Here, let me show you what kind of assumptions we like to make. Yeah. All right. First, why we can do that, why it is allowed to add reasonable assumptions. Okay, the reason is the original problem is very vague in certain part. Not sufficient information given in the original problem. So we like to fill that part. So, but it should be reasonable. Sounds reasonable. All right. So it does not change the nature of the original problem. Yeah. So the added assumptions should not alter the original problem significantly. Yeah. So then it's fair. It is, fair way to add those assumptions. Yeah. All right. So here, let me show you what kind of assumptions we like to add. First, for each addition operation, we assume the time used for one addition is 1 unit of time. How about that? Time, there is a certain amount of time. Yeah. How large it is, it depends on different machines, right? Yeah. Supercomputer, low end, that number could be different. But here, we just call 1 unit of time. How about that? That unit can change, can vary, depends on different computer. All right, yeah, first one. All right, but here we know that unit falls in this category, nanoseconds. In the modern computers, to do one addition is very fast. In a current PC, very fast. Okay, so certain number of nanoseconds, small number of nanoseconds, yeah. And we know 1 nanosecond equals 10 to the negative 9th second, or 1 billionth of 1 second. 1 billionth. Okay, yeah. So how little is that number, how fast for one addition in a current PC. Yeah. All right. The second assumption, each multiplication takes 10 units of time. We know doing multiplication is much slower than doing addition in a computer. But how much the ratio of the response time for these two operations? Approximately 1 to 10 ratio. Based on the real world situation, may not be exact, but pretty close. So for that reason, we just make assumption, 1 to 10 ratio. Yeah. Not very precise, but pretty fair assumptions. Yeah. So with these two assumptions, then we can do our analysis in a more accurate way. Yeah. So we can see the result for comparisons better in this way. Yeah. All right. So now, so after we add these two assumptions, so we get our discussion environment a little better, because we reduced ambiguity, right? We reduced ambiguity, so we make it clear, better for efficiency measure. Remember, so we need to work on efficiency measure. In that point of view, we are doing something good. All right. Next, so let's do some work. Now we need to count the number of additions. How many additions do we need in calculating this expression? First, we do not look at the multiplications. So we use two steps. The first step, count the number of additions. The second step, count number of multiplications. But in the first step, it looks pretty easy, right? Can you try yourself first? Can you get an answer by yourself? Counting number of additions. But here, there is some difficulty you may feel about it. What kind of difficulty? Because the number of term here, you see dot, dot, dot. How do you handle the dot, dot, dot here in this formula? We know the dot, dot, dot. A lot of information hidden in that dot, dot, dot. So how can we count something, some operations with this kind of vague formula? That dot, dot, dot means very vague, right? Do you have that question? Ask yourself first. If you have, then I like to give you the counting technique here. Let me, introduce this counting technique here. Counting, what kind of counting technique? First, in a discrete math, so think about the discrete math. Math 3000, right? You should have this math 3000 as the prerequisite. In that course, you need to learn many basic counting techniques, right? Many basic counting techniques. I don't know if you learn this or if you forget this basic technique. Let me give the name for it. Counting by reference. You may have the experience of this, but you may not see the name of this, because based on its nature, I gave it a name. So I create a name for it based on its nature. So later you will see its meaning. Counting by reference. So this method. Here I like to teach you this method first. So what's the essence of this method? Let me briefly describe it here. Then in the next video, I show you how to do it. All right, the essence of the method, pretty straightforward, like this. We need to discover one-to-one correspondence between two mathematical objects. So here I use some abstract terms, mathematical objects. What mathematical objects? Here we use two. The first one, number of plus signs. One plus sign corresponds to one addition, right? So we need to count the number of plus sign. So that is the first mathematical object, plus sign, right? The second, Then, because it is not quite easy to count the number of plus signs because it's hard to keep track of all the plus signs, right? How do you keep track of all the plus signs? Yeah, it's hard. Yeah. But I want to connect the plus sign to a second mathematical object. Yeah. So that is the coefficient a sub k. How about that? This is the second mathematical object. The first, second, two mathematical objects. Here, we want to get one-to-one correspondence between these two mathematical objects. Okay, so let me use a diagram to describe this method. We have two mathematical objects, object 1 and object 2. Okay, our goal, we want to count the number of object 1, but it is relatively hard. Okay, but now we want to connect these two objects in the one-to-one correspondence. That one-to-one correspondence is important. One-to-one correspondence. After we find this special relationship, then we can convert counting number of object 1, because it is relatively hard to count, to another equivalent problem, counting number of object 2, that is much easier to count. Okay, yep. So that's the basic idea for this counting by reference, this method. Okay, that's the idea there. Yeah. All right. Here, I just give you abstract description. Now, in my next video, number 2, I will show you how to apply this technique, counting by reference, to our current problem. All right, so let me stop our B.1 right here.